Okay.
Excellent. So the next speaker is Stefan Monnier. He's going to tell us something about normalizable types. So please go ahead.
Thank you. So as you see, I have also some margins on the sides. That's me screaming at the clouds that I want my 4x3 screen back. Anyway, so I'm not going to talk about screens today. So I'm going to talk about, yeah, I guess I have to stay here. I'm going to talk about quotient types. What are quotient types? Well, the type theory equivalent of quotient sets. I show here an example of quotient sets, but I assume you know what are quotient sets from quotient type from set theory. So in So in type theory, there is a more or less standard way to present quotient types, which is this way. You have the slash type constructor, which takes a base type t, and then some relation, binary relation on t that defines the equivalence relation on your quotient. And then you have a qin, which injects a value from the base type t into your quotient. Then you have your qeq, which lets you actually, it's the interesting part, it lets you get a proof that two values that are equivalent according to your equivalence are actually equal once they are injected into the quotient. So you have, if your x1 and x2 are related, which means they represent equivalent values, then you get that qin of x1 is equal to qin of x2. And this is pretty strong, and it only works because when you do your qelim, as you see here, you take a base, a value of your quotient type, and a function that takes the underlying value, a value of the underlying type t, and then produces something of type t prime, and it actually runs this function, giving you the t prime. And this only works because there's this p here, which guarantees that indeed you are going to be compatible with the relation, which means you're not going to actually pay attention to the differences between equivalent values. For example, you won't tell the difference between 2/3 and 6/9. Okay, so what do we want this for? Well, of course, we want this for just the same thing as we want to have quotient sets, right? But this is TyDe, so we don't only do proofs, we also write programs. So just to get a more concrete idea of why we would want that. So the usual equality in type theory, of course, is strong. It's structural equality. It really has to be the exact same term. And sometimes it's not really convenient to use a canonical representation. Sometimes, for example, you want to use named variable bindings, even though they don't have this canonicity property. They're more convenient for other purposes. Or sometimes you want to use, let's say, I don't know, a binary tree, and that represents an associative map, but without a canonical representation. Depending on the order in which you build your tree, you're not going to get the same tree. And usually in programming, it doesn't matter. But once you have dependent types, and this is the dependent type session, then you get into trouble. For example, you have a value of type key of some associative map where you first inserted C, then B, then A, but you need to pass it somewhere that set a key of where the map has first gotten A and then B and then C. And so the trees constructed from it aren't the same, and the type aren't the same. So you actually can't pass this value to the function. So using quotient types, you can inject your associative map into the quotient, explaining what is the relation between those different but equivalent maps. And QEQ then provides you with an actual proof that those two maps are equal, which lets you cast basically one of the value you have to the type you actually need it to have. Okay, so far so good. So, okay, what's interesting about it? Well, it turns out even though quotient sets and quotient types exist for a very long time, we still haven't really gotten it right. It's actually kind of difficult to get it right. It doesn't fit very, very well. So Lean is actually pretty happy with what they're using because they have some, maybe a more pragmatic point of view. But for example, in Coq, it's not used very often. And I think part of the reason why this is not used is because quotient types kind of imply the introduction of axioms, For example, it implies functional extensionality. So it slightly subtly changes your logic, which sometimes is okay, but sometimes it's not. So there are some corner cases like this. Also, because you have new axioms, you lose canonicity, which again occasionally is a problem. Another inconvenience, let's say, is that this QEQ gives you only a propositional equality. So it lets you prove that those two maps are equivalent, but the type checker will never on its own discover that the two maps are equivalent. So it always requires extra work, even in simple cases. So there are alternatives. Homotopy type theory, for example, tries to solve some of those problems. But of course, homotopy type theory has other problems in the context of programming. So I'm not going to consider this. But even other alternatives exist based on normalized types, typically. But those have their own set of troubles. For example, they tend to introduce inefficiencies at runtime, or they require unusual reduction rules, which make it more difficult to adapt to new systems, or they lack strong elimination or dependent elimination, meaning you can write programs with them, but you can't necessarily prove the properties of those programs. So what I propose here is actually a kind of quotient type that enjoys the following properties. So equivalent elements can be actually equal, like definitionally equal instead of just propositionally equal. It supports both strong and dependent elimination. I don't need any extra axiom. I don't actually change the logic. And the convertibility rule is standard, so I don't have any new proving to do for soundness, etc. And it's compiled to efficient code. Like there's no runtime cost for it. The only cost associated with it is that I can't define my equivalence classes by relations. I have to redefine them with a canonicalization function or a normalization function. And that's about it. Okay, I'm going to skip this. So what are normalized types, which I mentioned? It's something that I have not myself invented. It's been existing for a while. So there are a few different versions of it, but basically the fundamental idea is that you define your quotient as based on a canonicalization function. So your slash type now takes a base type t, and instead of a binary relation, it takes just a function from t to t, which returns the canonical representative for each equivalence class. You have your QIn is basically unchanged. You still have your QEQ, but it takes a slightly different form for proving that two elements are equivalent. Instead of saying that x1 and x2 are in the relation R, you just say that they are canonicalized to the same value. And your QLM looks fairly similar. It takes just a member of the quotient and then the function f, and it's reduced in the kind of obvious way, except that it first canonicalizes the value. Okay, so the nice part about normalized types is that it can be actually encoded into your language, which is why it doesn't need any extra axioms. And the encoding is really simple. It's trivial, basically. So is it too good to be true? Well, not really. It does work, It doesn't require any new axioms. It supports strong elimination. It gives you definitional equality for actually equivalent elements. And even better than that, I did not mention it before, but if you look at the definition of QLM, you'll see that it only takes two arguments. There's no third argument. You don't need to prove that your function obeys is compatible with your equivalence, because it only receives canonicalized versions of your values, so it can't actually distinguish equivalent elements. So this is great, right? Well, of course, there's a catch. The catch is that you have strong elimination, but you don't have dependent elimination. And for me, a more significant problem is that you actually have poor efficiency, because every time you inject your value into your quotient, you actually have to canonicalize it, to normalize it. And that if C is cheap, then all is fine. That's typically the case when you represent fractions, for example, and you want to keep them normalized pretty much all the time. But that's not always the case. If you have your associative maps, for example, you don't want to constantly normalize your tree, because that would defeat the purpose of the algorithm. So, and in many ways, if you look at the encoding, you'll see that actually the encoding is simpler than the original. So why use that? It's just, these are just smart constructors, and you can just go straight to the chase. Okay, so just to go back, we can try to look at what is the problem behind the dependent elimination there. If you try to keep this system of normalized type and add dependent elimination like I do here, you'll see that, okay, I can take an x, which is in the quotient, then a function that operates on the underlying value. So it takes the underlying value of type t, and it needs to return something of type t prime of some value of the quotient. And originally it should be the x outside, but within the function, it needs to be the representative in the quotient of your y. So it has to be this qn of y. And if you do that, the type makes sense. Intuitively, it seems correct. But if you try to actually look at your typing rules, then during proof, you'll see that it doesn't actually make sense. Because if you take just the type of QLM, QNE of applied to f, based on the definition of QLM dep, you'll see that it has to have type t prime of QNE. It's obviously the case. And if you do just one step of evaluation first, and then look at the type of the result, then it's going to be f applied to c of e. But this doesn't have this same type. You suddenly have called c beforehand. And it still works if c happens to be idempotent. And you'll see, well, it's a canonicalization function, right? So it should be idempotent. Most of the time it is. It doesn't have to be. We don't actually enforce it, but it's not a strong restriction. Well, it turns out that it actually is a very strong restriction because it doesn't just need to be idempotent, but the type checker needs to be able to discover this on its own. And type checkers aren't very clever usually. So, it's too severe a restriction. We can kind of work around it somehow, but I'm still not very happy with it. So Courtier in 2001 had a solution to that. I'm not going to get into the solution, just to summarize the problem. The main problem for me is that it's still inefficient because you still have to canonicalize your values all the time. So that is just unworkable for me. And also it introduces a bit of a complexity because you have kind of two different reduction rules, and you have to be careful to which one you use when to avoid basically double applications of your C function. So I don't actually like this solution, even though it kind of works, but mostly the problem is the inefficiency. So before solving the inefficiency, I provide an alternative solution to what Courtier did, which is a much simpler solution in my view, which is to say, well, I'll just introduce another constructor, qcan, which injects also a value into the quotient, but presumes that the argument is already canonical. And so the type of qcan is the same as qin, but now in QLM, I can use this qcan to avoid double application of the canonicalization function. The typing rules and the reduction rules are simple, and the result is that, yeah, we do avoid this double evaluation, and the system works, everyone's happy. Everyone's happy, dependent elimination works, but still, it's just a fancy dress for smart constructors, really. Like, we didn't actually gain anything compared to just using smart constructors. We're just, working hard to do nothing. And what I really want is not to have to canonicalize my values. So how do I recover efficiency? And now I have to really take a step back. Like, how can I recover my efficiency? Because I do want to normalize all the time during type checking in order to discover when two values are actually equivalent, so that I can get my definitional equality. Without this, the type checker will never notice that two things are definitionally equal. So it's indispensable to do it during type checking. But at runtime, I definitely don't want to do it. Actually, in my motivation case, at runtime, I actually can't because the reduction uses resources which are available at type checking time, but not at runtime. So I really need to separate the two and have reduction rules for type checking and reduction rules for runtime, which are distinct. And once we have those two different semantics, we need to make sure that the two semantics match. And to do that, I have to reintroduce in the QLM a proof of compatibility to make sure that our code actually doesn't pay attention to distinctions which should not be visible. So here's the QLM, the type of QLM I use. I have my X, which is the quotient value, my F, which takes a value from T to T prime, and then this proof here is a slightly different type than the original proof we got in the quotient types on the second slide. Now I have to prove that my function F treats canonical values in the same way as the non-canonicalized version of it, which is still basically the same notion of compatibility. And once I've done that, then the rest just falls through, and the proofs are very straightforward. I have Sanders' proof of the encoding, because the encoding is the trivial encoding I used for, I've shown before. And I also have a paper proof yet, not mechanized yet, of the erasure that I use for runtime, where I just completely erase all the quotient manipulation. So the normalization function is literally never called unless you yourself, of course, want to call it. And that still preserves the semantics. And along the way, I figured that first, it's really useful to add a constructor you never use. And second, that it is important to distinguish the reduction rules you have in type checking, the one you need for convertibility, from the one you need at runtime, which often can be implemented using just the same reduction rules, but sometimes it's really important to distinguish the two. Thank you very much.
Okay, are there any questions?
Am I right in thinking that there are some quotient types where this wouldn't work because you don't have decidable quotient? Like to write this normalization, you need to have a normal form, and you need to be able to compute that normal form.
Right, so it's not as general as the original quotient types, because I can only define them if I can come up with the normalization function. Yes, definitely. So it's a fairly large category of quotients, but it's not as wide as the other one. That is definitely true.
So I was also wondering, so you said you prove soundness. Did you also prove you still have decidable type checking? Or is that trivial?
It's trivial from the. I just add a few definitions, and it doesn't.
Yeah, but like you're adding new definitional equalities to the system in a sense, right?
Actually, not really. Yes, I do. I still have.
Do these definitional equalities preserve confluence?
So yeah, I have this QEQ, but actually during type checking, what I do is that the QIn really just applies the C. During type checking, I basically reduce by using the canonicalization function, just like I would do in the naive normalized type. And so I don't actually need at that point the QEQ.
So the thing I'm worried about a bit, right, is like sometimes you have to, during type checking, you have to evaluate open terms with 3 variables in them. And in that case, you cannot compute a normal form yet, right? And so you will do something, and then later on you might substitute something for these 3 variables, and suddenly now the normalization can compute further. So there is like, depending on which order you first substitute or you first normalize, you might get a different answer.
Right, but it's just because you cannot. I mean, it is just like the usual equality that you may have a definition of equality that's not true before substitution, and after substitution it becomes true. So it really is exactly the same situation. There's no. I don't actually need the QEQ really in my implementation. I just apply the C function, and the rest comes along.
Okay, I have to think about it a bit more. But, okay.
Basically, I have to pretend that Qn is not a canonicalization function itself, just so that at runtime I don't call it. But during type checking, I eagerly normalize all the time.
Yes, I get that. Yes.
So I think I didn't show it here, but basically I have a reduction rule. Oh no, I have it there. Yeah, yeah, here. So my reduction rule that says, well, actually qin just reduces to qcan that applies C. And then the QEQ is not needed anymore. I can just use REFL instead.
Yeah, but again, like I'm thinking about the more abstract situation where you cannot yet compute the normal form because there's something blocked.
Right, right.
And but maybe you have a hypothesis that, oh, these two terms or these two variables have the same normal form. Can I then reason about that? And does that suddenly apply a definitional equality? No.
No, because it doesn't magically try to figure that out. It's just, you have to use, in those cases, basically, you will not get your definitional equality, and instead you'll get a propositional equality, and you'll have to do the usual manipulations with propositional equality.
Right.
Yeah, okay. Yeah, I actually don't have a QEQ. I really use REFL instead in my implementation.
Hi, so if I had a different quotient type in the calculus with the ordinary rules for quotient type, would I be able to prove these are isomorphic to, I guess, given a canonicalization function, you could define the equivalence relation, and would you then be able, in the type theory, to prove that those are isomorphic?
I think so. I haven't tried, but yeah.
I hope so.
Yeah, exactly. I hope so. Yeah.
Okay.
Would be a good sanity check. Yeah.
Well, actually, you probably don't get, because of the definition equality, it might not work in both directions. But you can definitely encode these ones into the other ones. Yeah.
But you can do that with the unquotiented as well. So it's the other direction that's harder.
Yeah, but I'm not sure if that would work.
One more question? Yeah, go ahead.
So you had a slide with a list of reasons why cock users were unhappy. Could you go back to that, please?
There?
Right, so one of these was, in fact, I'm interested in all of them, but I particularly remember this breaks canonicity. Do you have anything to say about that? Do you solve that in any way?
No, it's just because it uses an axiom, there are cases where you can have a closed term, which just uses an axiom somewhere, and so the reduction doesn't go through.
But that's the same with your...
well, none with mine because I don't have axiom.
Oh, because you're axiom free at this
point.
Okay.
I really just encode my definition, provide definitions basically for all my elements.
Okay, so the cock users are going to be happy now, essentially, with your system.
I hope so.
Yeah, sure.
So can you give me an example of quotient types that don't have normalization functions?
Sorry?
Can you give me an example of quotient types without normalization functions?
Oh, no, actually, I'm not really interested in those.
Okay, fair enough.
I know they exist, but I guess my brain just prevents me from thinking of it.
Okay, well, let's thank the speaker again.